Good afternoon, everybody. It's a great pleasure to welcome Ron FOLMAN. Ron is somebody who just told me he did his master thesis and his PhD in a completely different area of high energy physics at Weizmann, also spending considerable time at CERN. But he had hobbies, and one of the hobbies was interest in foundations of quantum mechanics. So he visited at that time a PhD school around quantum foundations, and met there Anton, who invited him to come to Innsbruck, and he decided to do so for his postdoc in 1990, joining Anton's group and working on...
One coffee with Anton changed my life, so...
That's another one. And working there at atom interferometer, with interferometry, and then moved with Jörg later to Heidelberg and doing atom chips, which remains one of his fascinations. So this is unfortunately blocked. So after these postdoc positions, he took a position at Ben Gurion University, when he's since 2003 there, and led the Atom Chips group. He is also somebody very concerned with human rights and environmental activity involved. Also somebody who was a founder and the first director, but now you have to help me, of the quantum technology hub, let's say.
Whatever name, yes.
Yeah. And I learned also recently that he published a book which is called The Human Test, and it's about complex systems, all from the single qubit to the notion of consciousness, may I say so? Yeah. It just came in the States. And also somebody who got awards. It's a Lamb Medal, 2011, and then a Miller Visiting Scholar at Berkeley in 2013, and something with a Falling Walls Award in Berlin 2021. Okay, it's a great pleasure. Today, he will give a talk on experimental demonstration of something which might be called quantum equivalence principle. Please.
Thank you very much. Thank you very much, Aslav, for the invitation and the introduction. And it's always great to be here in Vienna. It's a very small room, so let's keep it really informal. Let's take advantage of the small size of the room. And if anybody wants to interrupt in the middle and ask a quick question, I will welcome that. Let's turn it into a nice discussion. So, the essence of my talk is actually this formula that you see here. M, you know what it is. G is just acceleration of gravity. H bar, you know what it is. And T is just the interferometer time. Okay? And this term here is what we set out to measure. And I hope that by the end of the talk, you'll understand this term much better. So the name is observation of the quantum equivalence principle for matter waves, or in a simpler name could be the measuring the phase of a freely falling object, and you'll understand what is the connection, I hope, by the end of the talk. The experiment has been done, and the results are now on the archive. It's still not a publication. It's under review right now, and you see here a long list of authors, one of which is here in the audience, and I hope you won't shout several times, "That's wrong, Ron," because, you know, like... Okay, so let's begin. Up, for some reason, yeah. So, before anything else, many of us are here in Vienna this week to celebrate Anton's 80th birthday. You already heard about my connection with Anton. He really changed the course of my academic career, and I am very happy he did that. And he brought me to Innsbruck, where I learned the business of cold atoms. So this is at Anton in Israel a few years ago. So I start the story by telling you how we got interested in the interface between general relativity or gravity and quantum mechanics. You know very well that this interface is problematic. It's one of the open questions of physics. We just don't know how these two pillars of modern physics work together. Both of them seem to work fine on their own, but there's yet no theoretical framework that unites them, and we would like to unite them. And some people think that the lack of this unification is so troubling, although we have been trying to do it theoretically for decades, that they think it's even a hint that at least one of these theories is fundamentally wrong. So you can hear such very strong statements, and that's why a lot of theoreticians are continuing to work on a framework called quantum gravity, but experimentalists are also going into the game and trying to provide experimental hints where we could find a way to unify or understand better how these two theories work together. So almost 15 years ago, we stumbled on a paper that came out of Vienna, actually, this paper that you see here, by Czaslaw and his group. And there I stumbled on this sentence that I really liked. So the observable they were talking about, or the measurement they were talking about, is a quantum effect that cannot be explained without the general relativistic notion of proper time. To understand the experiment, you have to think of both theories working together, and this caught my attention. And the idea was to do a clock interferometer, so to put a single clock in sort of a Mach-Zehnder, if you like, in a matter wave interferometer, and then to look at the interference pattern of this clock with itself. Okay? And the idea is that these two paths are at different distances from Earth, so they have different proper time because of gravitationally induced redshift. And therefore, you might say there will be some kind of schizophrenia of the clock because it doesn't know which is the correct proper time. Okay? So following this, we started to play around because we were at that time building atomic clocks actually for the industry. So we were interested in atomic clocks. So at that time, we said, let's play and try to put an atomic clock in a matter wave interferometer. It was never done before. And so we went forward to do that. I won't spend much time of it on this because this is not the topic of our talk, but just to tell you that this is how a simple atomic interferometer looks like in our lab. If this is time, this is spatial coordinate, then you have some pulses, magnetic gradient pulses that work on different internal spins. These are internal atom spins. This is a rubidium-87 atom. And so these are two internal states. We manipulate these states with some RF pulses that change the internal levels of the atom. And then with external magnetic gradients, like in the Stern-Gerlach experiment, we change the momentum of these two states, and we can do a Stern-Gerlach splitting. And so this is a simple atom interferometer, and then we turn it into a clock. These two wave packets that have the same spin, they expand. We turn them into two clocks. You can see the Bloch vector of these two clocks, green and red, these two clocks. Then they expand and interfere. We were looking at this. This is our observable. Because these clocks were not very good clocks, they were not optical standard clocks, we had to introduce synthetic redshift, not the real redshift of Earth. So this was a proof of principle experiment, still not working with the real redshift of Earth. But we could show that the prediction made in Vienna of visibility oscillating as a function of this proper time difference between the two clocks, this prediction from Vienna was correct. And now we're working in our lab on an ytterbium clock with the hope of doing this experiment really with the Earth redshift, which is, as you know, very small. Okay, so that's just the history. And of course, people are working on these strontium and ytterbium clocks, and people are already talking of very high accuracies for these clocks. Okay, so hopefully that could be done. Now, but today the topic is different. Today the topic is the quantum equivalence principle, and this would be the outline of my talk, but it's, of course, within the same interface of gravity and general relativity and quantum mechanics. So the outline will be what was done experimentally first. I think that's the basis for this discussion. Then, what are the possible theoretical interpretations of what was done experimentally? And time permitting, I will also show you another experiment that we are now, a very different experiment that we're now preparing in our lab, just very quickly, so you get a notion of where we're going. All right, so let's start. First of all, the tool. I already said the word or the term. I used the term Stern-Gerlach interferometer before. And indeed, we're already performing in the lab 10 years of Stern-Gerlach interferometry. So here you see some papers. I already talked to you about clock interferometry that we did. But also, by the way, the picture was also from one of the papers coming from Vienna. We started with a double slit type experiment, and you see here, these are atoms. You see here what you get from this double slit type experiment. We also measured geometric phase, like the Pancharatnam phase, which preceded the Berry phase that you all know, and so on and so forth. And now people are even using this Stern-Gerlach interferometry for metrology. And this is a paper that just came out a few weeks ago about geometric phase amplification in a clock interferometer for enhanced metrology. So this clock interferometry and geometric phase together, people are now hoping, and these are people from NIST, they are now hoping to use it for advanced or enhanced metrology. Okay, so Stern-Gerlach. I already explained this. We call it the half loop. The interference pattern comes from the expansion, natural expansion of these two wave packets. But what we're actually going to use in today's talk is this sequence, which we call the full loop. And why do we call it the full loop? Because if you here you had two magnetic gradient pulses, they come from the atom chip, by the way, from currents on the atom chip. Here you had 4 magnetic gradient pulses, so that the recombination of the two wave packets, you don't have to wait for this long time of flight for the natural expansion of the wave packets, but by force, you might say, you recombine the wave packets, and this is very important to fight against decoherence, because if you have strong decoherence, you have to really close the interferometer quickly, and you need to use force for that. So we have 2 additional magnetic gradients. It's actually also, some view this as an experiment in time irreversibility, because you're trying to do in the second half of the interferometer to completely undo in a symmetric way what happened in the first half of this interferometer. And at the end, instead of an interference pattern, special interference pattern, we measure here spin oscillations, spin population oscillations, as you see here. Okay, so this is what we will use in the rest of the talk. And artist's view of such an experiment is just the atom chip on the top. You have some current carrying wires, and they produce magnetic gradients, as you heard before. Here you have a BC. First of all, you make a BC. You cool it as much as you can, so it's really a point source, which is very important for interferometry. Then you use these gradients working on different spins in the atom to create a superposition, a spatial superposition. You split it, you bring it back, and that's the interferometer. So this is the half loop where you got a special interference pattern. Okay. So going forward, for 100 years now, almost 100 years, you see 1927, there have been predictions on what the phase of an accelerated particle would look like. And you see here what these predictions said, that it's going to be, if a particle accelerates with acceleration a, the phase is going to look like a to the power of 2 times t, that's the time of your experiment, to the power of 3. Okay? And it's very nice. I brought here a picture to go back to these old papers and to see what beautiful calculations they already did 100 years ago. But I myself was not aware of these predictions. And the person who made me aware of these predictions is Wolfgang, that is sitting here with us. And he said, Ron, there was a prediction 100 years ago. Why don't you test it? Now, this prediction was for an accelerated particle. My first question was, well, all the interferometers that have been done until now, they are all in the acceleration of Earth. But no one saw this t cubed. So why would I see it? And then the answer, Wolfgang said, was the following. Well, to see it, it cannot be that the two paths are under the same acceleration. To really see it, you need a differential acceleration, which all the interferometers so far did not have. Okay? And so we set out some time ago to try and do this Stern-Gerlach matter wave interferometer that I showed you before, the full loop, where the two spins are getting differential acceleration. Okay, and then we wanted to see if we observe this t cubed, and indeed, if this is the duration of the interferometer, or in this sense, it's of one of the pulses, the magnetic gradient pulses, so it's a fourth of the interferometer time, and this is the outcome of the observable, which is just the spin population. So you see the data coming here on top of the theory that was done in Ulm, in the group of Wolfgang, and you see we were surprised how good the data fit the theory. So really, we're now convinced that this theory, predictions from a long time ago about this thing was correct. But now the story only starts. The story starts with the following fact. First of all, we have to note that this interferometer, no wave packet was on a pure free fall, and no wave packet was purely stationary. So really, we didn't have here any fundamental frames of reference, which are typical free-falling or stationary in the lab frame. And so this interferometer was a nice demonstration, but it was not conducted in any one of the fundamental frames that typically people are talking about. And so we had to think of something else. And now, first I want to note here that this is the question I talked about before. Why didn't previous interferometers see it? And there were many measurements of gravity, of course, but in all these measurements, as I said before, there was no differential acceleration during most of the time, except for the kick, of course, that splits the wave packets. And differential acceleration due to gravity. No, so yes, so I write here that very few reported occurrences, I don't know if your paper is here, but there were very few reported occurrences, and please send me that paper, I should add it, but I went through all of them, I could not find anything where the two fundamental frames that I will show in a minute were really occupied. Okay, were used. All right, so the story continues with the fact that people then realized that if A, I told you about a prediction for an accelerated, but if A equals G, which is what happens in a freely falling particle, then this phase that we were talking about has to be this t cubed phase, must be also the phase of a freely falling object. Okay? So people have measured freely falling object for centuries. But the question is, how do you measure the phase of a freely falling object, okay? So I bring you quite a few papers that almost for a century have been writing about the phase of a freely falling object. And now the question is really how to perform it. A paper I was quite impressed with was this paper by Roger Penrose, Yvette, and Richard, where he actually talked about this freely falling object. This is his kind of picture. I think he drew it himself, actually. He told me he drew it himself, of a freely falling object. And he said, he called these two frames the Einsteinian perspective and the Newtonian perspective. The Newtonian perspective is the lab perspective, where you're not moving relative to Earth. And the Einsteinian perspective is a frame of reference that is falling relative to Earth. Remember these two names because we're going to use them. So I picked up these two names from his paper, and he said, if this is the description of a quantum system in one frame, and this is the description of the same quantum system in the other frame, then this will be the phase difference between them. Leave out now the linear with time phase. That gets canceled out in many cases, and we just left here with this t-cubed phase. So this story of the t-cubed phase is actually also now becoming the difference in phase between two very fundamental frames of reference. Now, when we understood that, then that became very much interesting because it connected us to the story of the equivalence principle. Okay? And now let's proceed to understand how. So, first of all, we just wanted to measure, before I tell you about the equivalence principle, I just want to tell you about measuring the phase of a freely falling object. How do you do it? Well, there's a big technological problem here, technical problem. You need an interferometer to measure a phase, we all know that. But you need an interferometer where one wave packet is freely falling with gravity, and the other wave packet to be in those two frames, Einsteinian and Newtonian frames, has to be completely static. So the question we have been asking ourselves in the last few years is, how do you close that loop? Okay? So as an experimentalist, one is falling. Just think about the problem. You have one atom. You split it into two wave packets, they're still together. One wave packet, you allow it to fall, like from that table in the Penrose paper. One wave packet is static. Now somehow you have to bring them back together to measure the phase. We actually started to think of all kinds of bouncing atomic mirrors to bring it back. But there were many technical details there that would not work for all kinds of reasons. We started to look at papers. If somebody has some suggestion, we found all kinds of suggestions from theoreticians, like this suggestion, but they were so unfeasible for us, in our eyes at least, that we almost gave up on the whole idea. Here, the idea is to start with a horizontal splitting, and then there is a rotation, a tilt to the vertical plane, the G plane, and then somehow you drop the other wave packet and you come here. The things we had to think about have to do with an effect called Humpty Dumpty, and this means that at the end, you have to worry about overlap in position to get some visibility in your interference pattern. You have to worry about this overlap. So overlap in position, overlap in momentum, overlap in size and shape, and even in angle, in rotation. You can all, if you're interested about Humpty Dumpty in rotation, you can also look at this paper from 2 years ago. So a lot of things to worry about, and we almost gave up because all these ideas that were available on the literature just didn't allow us to solve the technical problems. Okay, then we came up with this interferometer, which we call the quantum Galileo interferometer. So what was the idea? The idea was to, right after making the splitting, so you have a beam splitter here, right after making the splitting of the single atom into two wave packets. By the way, this is a BC, as I showed you before in the picture, but it's a dilute BC. There's almost no atom-atom interaction. We make sure it's dilute, so it's single atom physics, okay, single particle physics. That's the physics I'm going to talk about. There is hardly any atom-atom interaction. So after the splitting, we have a magnetic gradient giving a very strong pulse, very strong momentum kick to one of the wave packets, and then we change this state into a state that is non-sensitive to magnetic gradients. All this happens very quickly, in a few microseconds here, and then this state just goes into a ballistic motion, so it's in free fall all the time, and there is no coupling to our magnetic gradients. Whereas this guy here, this wave packet, is now sensitive to magnetic gradients, and we apply here a magnetic gradient that holds it static against gravity. Okay? So that's how, we call it the Gedanken experiment, because turning even this idea into reality, I'll show you later, was very problematic. Okay, So this was our Gedanken experiment, and we thought we could do it in this way. We put our atom chip, and we have the atom here. It's a distance of about 100 and something micrometer. Then we do all this operation that you see here. This is time, and this is height, but it's a 1D interferometer. So one of the wave packets goes up and goes down, meets here again, and then we take care of all these overlap issues, the Humpty Dumpty that I told you about before. Okay, that was the Gedanken experiment for us. Okay, this is, by the way, a unique interferometer because most other interferometers, or all interferometers I know at least, matter wave interferometers, are either free space or guided. And this one actually is using both techniques at once, simultaneously. So this you might call is guided because it has a potential acting on it the whole time. And this one is free space. There's no potential acting on it. So it's hybrid interferometer in this sense. All right. So it's very different from the Ramsey-Bourdais and Kasevich-Chu, but I don't have time to go into these details. All right, let's go forward. So, an important anecdote for you to notice, we don't use lasers. Okay, so all this is in the dark. It's very important because when you take a Kasevich-Chu or when you take a Ramsey-Bourdais, which actually the laser pulses are the ones doing the splitting in the mirrors, when you do transformations from frame to frame, you have to do also transformations on the Maxwell waves, which are the electromagnetic waves. Otherwise, you just don't get the thing to work. If you want it to make sense in all frames, you have to also do the transformations on the electromagnetic waves. Here, not. Here, it's all about, you can say that it's purely de Broglie waves, okay? So it's very interesting in that sense. This is a calculation that was done by Wolfgang from the two different frames of reference that you see here. And you see here the Newtonian and Einsteinian. It's beautiful to see, here is a calculation of the action. And it's beautiful to see that you come out with exactly the same action up to a sign, as you see here. And since the interferometry is a cosine function, it doesn't care about the sign. And it's very nice to see that for there's an exact symmetry between the point of view from both frames of reference. All right. Yes? Well, we can argue about that later. We did a very accurate calculation, and G at least appears always, and that's why we claim that the gravitational mass, if G appears, the gravitational mass, of course, has to appear. But let's take this discussion afterwards. It's a long discussion, but all the calculations are there. Okay. So, a cool way to calculate the phase. I showed you this phase in my cover slide, okay? But what is the simplest way to calculate this phase? It comes from this equation that you saw from the Roger Penrose paper. You saw this equation before in Roger's paper. And this is the difference between the wave function of the system in the Newtonian frame and in the Einsteinian frame. And you get this phase that some call the gauge phase, which you already saw before, which is this. How can we calculate now this, which is the phase that we're looking for? Well, you just split it into two calculations. You can start from t equals 0 in the middle and go, one interferometer goes to minus t. And you can start from this t equals 0 in the center and go to plus t. These are these two calculations, and for one you get a minus, for one you get a plus, because of this odd power here. And then you have to add them to get the full interferometer phase, and when you add them, you are getting this, with a minus sign, you're getting here exactly this phase. So this is the simplest, I think also most intuitive way to calculate this just from this transformation that I showed you before. Okay, now for the experiment itself, which is much more complicated than the Gedanken experiment. I tried to briefly go through it. How much time, by the way, do you usually take for the seminar? Okay. All right. Okay, so maybe we take at some point a 5-minute break so everybody that wants to leave can leave, and then we can continue with some people who are interested in a deeper discussion. Okay, so the experiment is quite complicated. It took us several years to understand all the problems. So let me briefly take you through it. So this Gedanken experiment only happens here in the middle. We start with the BEC in some internal states, actually at the 2,2 state of the rubidium. We release the trap. It's a magnetic trap on the chip. We release the trap. It gives it some kick in, you see there's some kick in height. Then we apply another cooling, which is called, in atom physics, delta kick cooling, to win some more in temperature. And then we apply a microwave pulse that puts this in a superposition of states. This is our qubit, the interferometric qubits between the 1, 0 and the 2, 1. So when I talk about a state that is to first order, independent or insensitive to magnetic field gradients, it's this state. And when I talk about a state that is sensitive, it's this state. And so we have a superposition now of these two states. The whole thing is in some trajectory. There is still nothing splitting this superposition. And now these red areas are the magnetic gradient pulses. So the first magnetic gradient pulse comes here, splits these two spin states, and gives momentum for the ballistic motion. But immediately after that, there is a pi pulse reversing. You see it here in the zoom in, reverses the state. So now this guy is in the magnetic sensitive states, whereas this guy is in non-sensitive state. And so this pi pulse does that. After that, the whole thing is reversed. So you have another pi pulse and another magnetic gradient pulse to stop the relative momentum, the relative motion for that overlap that I talked about before. You have to zero the relative momentum for that Humpty Dumpty problem. And then at some point, you have another pi over 2 to mix the spins, and you can make a measurement. And actually, we make the measurement by another Stern-Gerlach pulse that separates them in real space, the spins in real space. Here I didn't mention this little pulse here that is a long pulse. This pulse is the holding pulse, which actually is the gradient that is exactly equal to gravity. If it's not equal to gravity, so mg has to be exactly, the mg of that atom has to be exactly equal to the gradient, magnetic gradient force times mu, of course. Otherwise, we were not going to get that static position. It's going to go down or going to be up. So actually, you might say that this gradient is weighing the atom, and so from that we can even measure, just because we know this gradient very accurately. If we know m, we know g. And then this holding pulse, you see it here. And I think I now described to you the complete sequence. You see in millisecond, the interferometer is only about 2 milliseconds. Okay? And we took advantage of the fact that we're very close to the atom chip, so we can do everything very quickly, even the magnetic pulses. If you use coils, you have inductance, it's going to be very long. Here we just use a current carrying wire, no inductance, very quick on, off of that magnetic gradient. Okay, this is the chip that we used. And one more thing I should note is that when you do the analytical prediction, This was the phase of the Gedanken experiment, but you have to add here the time of the kick. T kick is the time of this pulse. It's not zero. It's not a delta function. And you have to also add the delay time. Because of electronics, we had to introduce a delay time, Td, which is this delay that you see here between the different magnetic pulses. When you add all this, you get this analytic phase prediction. But when you go for Td going to zero, and we did everything we could to take these numbers very close to zero, you retrieve your Gedanken experiment prediction. All right. And of course, we wanted to make sure that the interferometer is well behaved, so we took pictures everywhere along the path. We did a lot of numerics that, to make sure that we understand the interferometer, but we also took measurements midway of the trajectories just to make sure that the trajectories are really as we expect. So for those of you that are experimentalists, I should note that aside from inventing this QGI, we had to use all kinds of tricks for this to work. I told you it took several years. For example, only if we gave the gradients with a quadruple field could we get visibility from this interferometer. And the trick here is that a quadruple field, although it gives you high gradients, it has close to zero magnetic field. And that reduced a lot the phase noise we got from magnetic fluctuations. This is one trick. We had to use a very small cloud. So this is called initial point source to get visibility. The atom chip trap, which is a high gradient trap, it's a tight trap, took care of that. We could get a very small cloud with this high gradient. So we had a very stable initial source. Delta cooling I already mentioned. We had to use dynamic decoupling. Yeah, I guess you all know what it is. So this was our sequence to get rid of all kinds of gradients, spurious gradients that we had in the chamber. And last but not least, everything was done on batteries. Doesn't matter how many filters we put on the wall, electricity, it never worked. So at the end of the day, only batteries could get the thing to work. Okay, so the results. So this is how the data looks like, something like 13 oscillations. And this is how the CCD images, after the last splitting, Stern-Gerlach imaging or detection that I told you about takes place. You get on your CCD these images of the two wave packets, and you see how they oscillate, and from these oscillations, we get this data. And finally, by fitting this data, we get this graph. And what do we see here? Now let me spend some time on this graph so you understand it. The y-axis here is just the phase of these oscillations, okay? Here it's just time, okay? And now what you see here is how the phase evolves with time. And we have it's quite busy, so let me just go through the legend. First of all, the red curve is data. And then you have several additions to it. First of all, you have the green dots, which also appear here in this residual plot, because it's hard to see, so we put a residual plot. But the red points are numerical simulations that took into account tons of stuff, like, for example, atom-atom interaction. I said it's very small, but we took it into account. Relative size of the wave packets. They're going through curved magnetic gradients, so they were focused to different levels. So there's relative rotation of the wave packets. There's so many things to take into the numerical that I was shocked that the numerics was actually accurate. So the green dots are the numerical simulation. Then you have this analytical approximation that I showed you before with the TD and T kick. This is this, and last but not least, you have the Gedanken experiment prediction, which is this black line, which is furthest from the data. We also have these yellow lines. We changed the theory by 0.5% just to show that any theoretical deviation from this cubic power law is going to take us very far away from the data. So the conclusion of all that, if you look here at the residuals, that are only a few radians out of these 80 radians that the data accumulates, the conclusion is that with high likelihood, I would say, we have really observed the t-cubed, the predicted t-cubed phase. And by the way, the green dots are not fine-tuned. The guy who did them, his name is Yoni Yaffe, he always asks me to emphasize that this was a blind numerics. Okay? He did not fine-tune anything. He took the nominal values of the parameters in the lab, which have, of course, systematics on them and uncertainties on them and so on, put them in his numerics, and that's what he called blind numerics, and the residuals are very small. After that, just to show that he could fine-tune, the blue dots here are fine-tune numerics. He could gain a little bit more in his accuracy when he actually moved a little bit the values to fine-tune his numerics. Okay, so these are the results. This is what we saw, and so far what we've proved, I think we confirmed the phase of a freely falling wave packet. Note that I don't mention here yet the quantum equivalence principle. We have confirmed that equation we saw in the paper by Roger Penrose and colleagues between the transformation of the Einsteinian, of a quantum system between the Einsteinian and the Newtonian frames. And also, you could say that when we looked at these two wave packets, we showed that it's completely symmetric, also from the calculation of Wolfgang of the action. Completely symmetric, so it doesn't matter where you sit, on which wave packet, you see exactly the same picture the other wave packet doing. Completely symmetric interferometer in terms of matter waves. Okay, now let's go to theory. So you saw the basic theory, but now I want to go into the theory of the quantum equivalence principle. So the Einstein equivalence principle you all know. This is probably the most common definition of that equivalence principle, although there are many, many other versions. And he, as you see here, connected between the situation of a homogeneous gravitational field, a system that is at rest, let's say in the lab on Earth, and it's indistinguishable for something that is, let's say, in deep space, in a spaceship in deep space, no gravity, but acceleration A of the spaceship. And he said these were indistinguishable. Now, the talk about the quantum equivalence principle and the connection to the t-cubed phase goes back quite a long way. And I'm not sure I found all the papers, but the first paper, as far as I know, that talked about the connection between the t-cubed and the phase and the quantum equivalence principle was in this paper by Danny Greenberger. I actually found this nice picture of him celebrating his 19th birthday. I think it was here in Vienna, if I'm not mistaken. And so this paper is also widely cited in all the other papers that I'm going to mention here. Quite a few papers talk about this connection between t-cubed and the equivalence principle. And let me know just three that I liked. Naunberg talked about it, 2016. And here again from Chaslav Group, 2019. And here from Marletto and Vedral in Oxford in 2020. But as I said, many people have dealt with this connection between the t-cubed and the quantum equivalence principle. And so I would say this is already quite robust, at least in the minds of all these people that wrote these papers. So what is the main point when you want to make a connection between the t-cubed, this is very important now, between the t-cubed and the quantum equivalence principle? Now, if you have fallen asleep so far, for all the theoreticians who fell asleep in the experimental part, now please wake up. This is the main theory point. So, if EP is correct, equivalence principle is correct, then this is what the equivalence principle is saying. I just showed you the definition. And if this is correct, then if our spaceship that Einstein talked about is the Einsteinian frame of reference now falling above Earth, so there is gravity, it's now falling with gravity above Earth, then if this is correct, then this wave packet, ballistic wave packet, in this Einsteinian frame that is freely falling, there are no forces on it, and there is no phase evolution on that wave packet beyond, of course, the free wave packet evolution phase that all wave packets have, which is identical in our interferometer for both paths. So let's neglect that, and I won't mention that anymore. But there are no forces, and that's a consequence of the equivalence principle because of this equality. Now, if this is correct, then you can go to equation 1 and say, aha, but equation 1 that I showed you already several times tells us that when viewed from the lab frame, Newtonian frame, not from the Einsteinian frame, this ballistic wave packet will present a phase depending on t cubed. That we get not from the equivalence principle, but that we get from this equation 1. The equivalence principle allowed us to say that there is no phase that we don't know about in the ballistic wave packet. And so now, the conclusion from this is that the t cubed phase that if we observe it in the lab frame, which is what we were looking for, is an exact result of the EP. That is the simplest. There were many different arguments in the different papers for this connection between t cubed and the equivalence principle, each one with his own taste. But for me, this is the simplest argument that I found, and this is indeed what we measured. So, to conclude, I want to have a few minutes just to show you the next experiment. That's my outlook. So I want to conclude already now, but we'll leave time for questions. So we realized a new type of interferometer. As you heard, it's a hybrid type of interferometer that is half a free space interferometer and half guided. We've confirmed the phase of a freely falling wave packet. That's this 100-year-old prediction. We confirmed the transformation between the Einsteinian and the Newtonian frames of reference. Again, there are many papers that dealt with this transformation. That's the equation 1, as I called it. And we showed that the equivalence principle between the E and N, of the entire superposition, because of the symmetry of the interferometer. And finally, the connection to the quantum equivalence principle is that if indeed MIA is indistinguishable from MGG, that comes from the equivalence principle, then you expect the T cube phase difference, and this is what we measured, and this is indeed an outcome. It's a quantum system, and that's why we're allowed to call it the quantum equivalence principle. Okay, in the few minutes I have left before questions, just a few slides that I think will interest you. Okay, I forgot, sorry. I have to mention, of course, that after our paper came out on the archive, it's still not published as I noted, there was a comment made on the archive, an interesting comment. If people are interested in this experiment, I think it's nice to read. And of course, we also answered this comment a little bit later. If you're really interested, read the paper, read the comment, read the reply to the comment. I think after all that, you'll really know the nuts and bolts of this experiment. So that's nice that there's some discussion going on online about these experiments. Okay, so an outlook. Well, we're continuing to do all these kind of, let's call them special kinds of interferometer, to invent new kinds of interferometer with rubidium atoms, because by now we have more than 10 years of experience with these interferometers. But at the same time, we would like to go to much higher masses. Okay, and this is something Vienna, of course, is also Markus Arndt and Markus Aspelmeier. Groups all over the world are trying very hard to go into this business of quantum states or non-classical states with massive objects. There's a lot of new experiments that could be done. And so the idea here is to have a Stern-Gerlach experiment working on the spin, just like we did with the rubidium atom. It's the same Stern-Gerlach full loop that I showed you before. But now shoot in a nanodiamond. This is a nanodiamond with one spin in the middle. And then you can test all kinds of foundations of quantum mechanics, like the continuous spontaneous localization, fifth force, Diossi-Penrose collapse, many theories connected to quantum mechanics. Well, fifth force is gravity more related, but also on the interface, which is what interests us, There are papers coming out saying, look, if you have this kind of interferometer, you can also check entanglement, gravitational induced entanglement. There are some filters here where only gravity remains as the dominant force between these two wave packets. So now there are two nanodiamonds, each one with its own interferometer. They happen at the same time but very close to each other. And the only interaction is gravitational. You then do a Bell-type measurement on the spin. And if you see entanglement, you say, aha, gravity-induced entanglement. And if gravity-induced entanglement, the interpretation is, and again, there's no consensus on that, but the interpretation, at least of these authors, is that you have proven that gravity is quantized. And these are not the only authors that suggested this. There are more papers and so on. Just to show you how it looks like in the lab, you see here the particle. This is a Paul trap. It's now going to a chip. Again, we work with chips because it's much more accurate, much faster. So the idea is to have here in this gap, 2 millimeter gap between these two, the interferometer happens here. This nanodiamond interferometer, here are the nanodiamonds that we grow here. They have to be very accurate. And there are all kinds of techniques how to cool down these particles. You cannot use these laser cooling, which we use with atoms. But here in Vienna and in other places, people have found beautiful methods, feedback cooling, to cool down these particles, and that's what we're doing. And these chips that we made already captured as a test in Ferdinand's lab laser-cooled ions, and this is the wire that is going to give the very strong magnetic gradient that you need to move these massive object, 10 to the minus 15 kilogram, very massive object. 10 orders of magnitude more massive than our rubidium atom. We're jumping now 10 orders of magnitude in the lab. Okay, that's a big jump. And then that's where we are. It'll take time. It's not going to be finished tomorrow, yeah? But it's a fascinating project. Okay, and again, if it succeeds, thanks to the groundbreaking work of all the people who did this work, Aspermeyer, Novotny in Zurich, Barker in London, Stickler in Ulm now, Novotny for rotation cooling, Morley Hetet. I won't go through all the people. Many people are contributing to this effort around the world. All of them, all of this great work is bringing us closer to realizing the above. And just two interesting points I want to show you about the new theory that needs to be done for these experiments. These experiments need new theory. For example, Carsten Henkel from Potsdam found out that even if you completely decouple from the external environment, you're going to have horrible decoherence from the internal environment, the phonons. Okay? So for anybody interested in putting a car in a superposition or a spaceship in a superposition, there are a lot of people dreaming about that. So here's the object size, and you see that as you go above the centimeter scale, you're running into problems. I don't have time to show you, but it's much worse than black body radiation or any other kind of environmental decoherence that we know. The internal decoherence will kill us. And so this is very interesting, and the latest calculation was published last year. Look at it, and I think it's very fundamental. And another paper that I think you should look at has to do with the Humpty Dumpty. This is one of the authors, inventors of the Humpty Dumpty experiment, Marlon Scully. These are three gentlemen that in the 80s coined the term. And the idea is that if you don't close the loop perfectly, your coherence or your visibility of your experiments drop exponentially with this lack of accuracy in closing in momentum or in position or in rotation or whatever, the size of the wave packet, whatever. And here's a paper we published 2 years ago. Jonathan Yaffe did the calculation that even if you perfectly close the interferometer in space, if it's not perfectly closed in rotation space, just different rotations, completely orthogonal systems, which path information, you will not see visibility. So we need to cool also rotation, not only center of mass. No one has ever done it, to cool all 6 degrees of freedom to the ground state. Yeah, not even close. So that's what we need to do. It's very hard. And here you see coherence, versus the time of the interferometer, you see the drop. Okay, last but and definitely least. So to finish on a lighter note, I'm going to give you a 30-second advertisement. If you don't like advertisements, close your eyes now and your ears. Okay. So, for the last 10 years, I developed a strange hobby. When the experiment doesn't work, you're frustrated. You need to have some hobbies to vent your anger, your frustration. So I started to read 10 years ago a lot of papers on consciousness. You know, the question, who am I? Sort of a nice question. And so I was surprised to find that it's, of course, highly speculative, but quite a bit of good theoretical and experimental work is already going on. And so after 10 years of reading, I don't know, hundreds of papers and books, I decided to write a popular book about it, and it came out a few weeks ago. So you're welcome to read it. It's called The Human Test, and it's popular level, but with hundreds of scientific references. And yeah, I enjoyed writing it very much, and it, I think, a little bit illuminates at least what is being done now, beautiful work that is being done now. The field is still, I would say, diverging, but still beautiful work is being done by scientists all around the world. And I put some speculative hypotheses also in this book. All right, so let me thank the people who did the experiments. This is the team in the lab. And some of them, as you see, have moved on. Of course, thank you to the many, many theoreticians that have worked with us in the past decades on all these experiments and the funding agencies. And I thank you for your attention. Thank you very much.
Okay, so we are open for questions. Yes, please.
If nobody says anything, I always can say something. So, Ron, the remark you made about consciousness
Yes.
is a very deep one in connection with quantum mechanics. You might have thought, well, maybe that's esoteric. Maybe it is esoteric, but Wigner was a big proponent of the consciousness and the conscient observer. Now, Wheeler, on the other hand, was strictly against it, but Wigner was a big proponent.
I quote Wigner in the book.
Yeah, you did
I quote him in the book. I quote many physicists in the book, including Anton and, of course, Roger Penrose with many of his ideas. So Schrödinger talked about free will and so on. So a lot of quantum physicists Aronov is talking a lot about it, are going into this game of thinking about consciousness. It's fascinating, and the book includes a lot of discussion about how quantum mechanics may be taking a part in our consciousness. Yeah, I think there is a strong connection there.
Are there any questions? Not even from the people who write comments? wait, now you are not somebody first.
Hello. So I wanted to ask about the role of the Einstein's equivalence principle here and the difference with the weak equivalence principle. In the sense that the Einstein equivalence principle, as you were saying, means that we can transform gravity away locally.
Yeah.
And this has some consequences, and one of these is universality of free fall, which is what you write, but it's not the only consequence, right? Like, for example, we have gravitational time dilation. And it seems to me that in this test, what you're testing is the weak equivalence principle, in the sense that you're testing universality of free fall. So, for example, you could get the same prediction just with a Newtonian theory, just with a potential, and that would give the same results. So you don't need GR. So there are effects beyond that you could test. And this is my first question, like if you can comment on this. Second one is that what you could test that with.
Maybe I answer the first one before I forget it, because I'm old already. You know, old people, it's hard to remember. So, well, I showed you why I think this is directly a consequence, the T cubed, and there are by now, I think, dozens of papers claiming the same thing, that this T cubed is directly connected to the equivalence principle. Of course, this is open for discussion, and that's fine. But I think that the interpretation I gave of why this is a direct consequence of the equivalence principle holds. And without that, there is really, that is the most direct link between the equivalence principle. Now you use the word weak. Now in the entire paper, there were many weak equivalence principles in the paper. I threw them all out. And the reason why I threw them all out is because as I was reading the literature, I found that there are so many different definitions of what is the weak equivalence principle that I said, if I myself am getting confused with the definition of which definition is correct of the weak, I don't want to put it in the paper, and so the whole paper does not use that term. We say explicitly what we are assuming to be correct, and that is that the inertial mass and the gravitational mass are equivalent. We said that already in the beginning. And from there, everything else follows. I think that if you can assume that they're not, or not proven, well, we give a lot of references to all the experiments that have proven them up to some accuracy to be equivalent. But you can say it's not enough for you, and there is maybe some definition. Deviation, yes. We started from the assumption that many people call the weak equivalence principle, that the two masses are equivalent, yes.
My second question was on how to test something that I think comes out of Einstein's equivalence principle, that is not only that the mass are equivalent, for example, time dilation. And I think the setup that you were describing before can do that with this atomic clock in superposition of different heights.
Yes, that was the idea of that experiment.
So I wanted to ask if you're still working on this, and if you have an idea of a time frame where you can measure the time dilation of the Earth.
So that's a great question. I think that the development of clocks is so fast that, as I showed in this reference from Jun Yi, they're already brave enough to put in publications in the abstract 10 to the minus 21. We are working on a terbium clock. Some people are working on a strontium clock, but we definitely hope that these kind of clocks will make it feasible. Timeline, it's very hard. The clocks are moving very quickly forward. The problem is the technology of combining these clocks with a spatial interferometer. You need enough splitting. Even for those kind of clocks, you need enough splitting, and even to get, the splitting we got here was only a few micrometers between the two paths. For these clocks, even the optical clocks, to get a significant readout or signal, you have to have a splitting of centimeters, and coherence time of this interferometer, not a millisecond like we had, but closer to hundreds of milliseconds. So to combine these kinds of numbers, which people independently got already for atomic interferometers, I mean, the state of the art for splitting is 0.5 meter in Stanford, Mark Kasevich, but people have got it. But to combine that with the clock technology, and the clock technology is quite complex, that is the question. What is the timeline for that? It will be achieved. Whether it's a year or 10 years, I'm not sure, but definitely in that time frame.
Before I hand to Peter, I very like this exchange because it clarifies a lot of things. But maybe I can add how I see that so far there was a test of MEI equal to mg, but the two branches or amplitudes were such that they were, at least to my knowledge, I'm excusing myself, but at least were always at the same acceleration. And here you do test the same relation, but where the branches are in a different one. Okay, and then of course there is much room for extending, and I'm happy to, I'm really what Carlos said. And so now the question is always like how you formulate this. Like as you said, there are many formulations. Okay, and so one of them I think is really going back to the time of original formulation, like of the Einstein equivalence principle. This was like this idea of the, and Einstein himself admitted that this was like enlightenment. The idea that if you're in a small elevator freely falling, nothing, you will ever see a difference from being far away from anything else. And I think we all share now this view that you don't need to go beyond that in order to talk about quantum equivalence principle. If you can think about your freely falling atom as a small laboratory in which you, of course, should be able to perform some experiments. That's why idea that you have a clock or something inside this. And then I'm alone from this idea that you can put yourself in the quantum reference frame. Even if it is a superposition, there are transformations. There is a whole people working on this thing. Alone from this idea that if you would be able to move into this reference frame of the freely falling, this is not what you were talking, because you are still talking about Einstein and Newtonian reference frame, which are classical for both amplitudes. I'm saying a very quantum coherent movement.
So your reference frame is a superposition.
It's a superposition.
Yeah.
Then, and assuming that locally you have a flatness, or like Minkowski space-time, you can go back to the laboratory frame, and then you see t to the power 3, and also effects that we will see on the clock. And I think this will be a nice way to go forward with your experiments, beautiful experiments. I don't know what you want to comment. If you want, I leave you. If not, I give to Peter,
No, please give it to Peter. It's fine.
Okay.
So can you go back to the Kennard slide?
To the?
Kennard phase slide?
Kennard phase. Yes, let's go back. Let's see. That was in the theory part. Just a minute. Let's see. Wait, just a minute. I think it was in the theory part.
I think very in the beginning.
Maybe it was in the beginning. Sorry, you're right. Sorry. Well, I'll just go quickly. Let's see. Here?
No, I can't further back.
I know what you're. Oh, here.
No,
That
this one.
that was the first time I mentioned Kennard, I think, in the talk.
So my comment is the magnetic interaction is spin dependent, right? So it can create differential acceleration or relative acceleration between the arms of the superposition.
Yes.
A uniform gravitational field cannot create relative acceleration. That's why it cannot create such a phase shift from a uniform gravitational field.
And so, what is the bottom line of your comment?
I mean, your quadratic. So I mean, writing it as a quadratic term, so a quadratic of some acceleration. What is this acceleration? And the only relative acceleration in your experiment is the one from the magnetic interaction, which is spin dependent.
Well, no. The other way to tell exactly what you're saying, yes, the other way to say exactly what you're saying is that, of course, I had to have a differential force in my lab because I had to keep, that's the hybrid interferometer, I had to keep one wave packet in the Newtonian frame. The only way to do that in a gravitational field is to use a force, of course, but that is trivial. But the point of the matter is that the fact that we use the force, that there was a force in the lab, let me give you an example. And with this, I will end. I think Wolfgang also wants to say something. Newton observed, he sat on the ground and observed an apple falling. We can describe this, for him it was a measurement of gravity. We can describe exactly the same experiment that we all learned from textbook in a completely different way. I come and say he did not observe gravity. What he observed actually were the electromagnetic forces that the atoms on the ground were applying on his body to keep him static in the gravitational field. That was what he observed. This is an exact analogy to our experiment. So you can say, well, what held Newton's behind static in the gravitational field, those atoms of the dirt of the ground, the electromagnetic repulsion, is exactly the magnetic gradient that we applied on the static wave packet, exactly the same. And our ballistic wave packet is Newton's apple. And so we could look at this picture and say, well, if Newton did not measure gravity with the apple, it was not an observation of gravity, but an observation of some force on his body, then okay. But This is not the case, I think. I think that after, I don't know, many dozens or hundreds of experiments measuring gravity, starting from, you know, Galileo and Newton, I think the story, how it's told, that it's not the atoms holding the static reference frame, like the Pisa Tower holding Galileo in place. No, but it enabled him to measure gravity, and he did measure gravity. I think that is the right way to tell the story. But of course, in physics, you can tell stories in different ways. But one more thing that I have to say, and if you ask, then I even prepared a slide for it, which I didn't show so far. But since you asked, I think, because it's really an interesting discussion, what language do we use? But sometimes physics tells us, no, we don't care about the language. And it tells us what the answer is. And the answer is, I prepared a slide for it. Wait for it, wait for it, wait for it. Sorry, just a minute. It's here. So, this is the results that you're talking about. Yeah, this is the result where the phase comes from the magnetic field. But what is not written clearly in your comment is the fact that this result is correct only in a very special case. It's not general result. It's correct only in a very special case, and we showed it in our reply. It's correct only when this equality exists. And this equality is exactly the two languages I was now talking about with Newton. Exactly, because if you understand that this result is a special case that exists only, we call it, by the way, the levitation condition, only when this result exists, you know that you can speak also with this language. You're measuring G, just like Newton measured G or Galileo, but I claim that this language, physics teaches us that this language is the preferred language, more general language. Why? Because of the next slide. The next slide has to do with the residual acceleration, okay? So the residual acceleration just means that there is no exact cancellation of gravity, and that's what actually happens in the experiment. I showed you the trajectories. There's always some residual, and if you look at the residual acceleration, which is not, you talk about it in words, but it's not really written down, but we wrote it down. The residual acceleration always includes gravity. You can never take it out. You can never choose a language in which it doesn't appear. So this is the more general language because it takes care of all cases, not only the special case that you're referring to. And then you see that you always, in the general case, you always have gravity in there. So that is my answer. I would always prefer the language that is more general, is not focused on a special case, but treats all cases. And in this case, it's the language in which I have a G, the gravitational field or gravitational acceleration in there. You cannot take it out. You cannot factor it out in any language if you talk about this A residual. I hope this clarifies.
I mean, there are many points to be made, but I mean, the first point I would like to make.
Just 1 second. I would love to have this discussion also over beer. No, it's a good discussion, but maybe we give people the chance to escape. Those who want to. You see, already volunteers, and yeah, okay, okay, because we are past our time. And when I'm in the audience, I always appreciate that they give me a chance to escape. So thank you for coming. Thank you for coming. I'm here for the whole week until Saturday.